It's okay? I mean, what is the secret of making it cut out? I haven't, it's just random.
Okay, so
Okay.
sorry, I forgot to introduce Edward Grant from the University of British Columbia, who will speak about many-body physics with ultra-cold plasma.
Thank you. So I guess I should preface my remarks by saying that I'm an experimentalist, and this will be a talk that's a little bit about experiment, but mostly about physical interpretation. And so what I'm going to try and do with all of the theory that I present is I'll try and give you a physical feeling of what we think is going on in this system. We've also heard this morning already, and certainly I think we're going to hear all week, about thermalization, about eigenstate thermalization, about the relaxation of quantum mechanical systems. And this subject has certainly become important in the years since Basco's paper, and this has motivated a great number of, or a handful, I should say, a handful of experiments. And these experiments have attracted a great deal of attention. They've appeared in very impactful journals, and they're highly regarded. So, yeah, good. Now, in every one of these cases, these are highly engineered examples that appear to confirm theoretical predictions of quantum states in which transport is suppressed. I mean, they're argued to represent cases of many-body localization. I will point out that in every one of these cases, these are atom-atom interactions. They're weak dipolar cases of weak dipolar coupling and weak disorder created by optical lattices, so by optical fields. One wonders, this begs the question, in systems of stronger interactions and stronger disorder, can the locally emergent conservation laws that develop and seemingly affect many-body localization, can these drive the evolving quantum system to naturally form a state of many-body localization? So that's a question I'd like to ask with my talk this morning. I'd like to begin by just presenting you with a hypothetical system. So the hypothetical system I'd like you all to think about is highly disordered, ultra-cold, dipolar gas of Rydberg molecules. These are high-N, where's my pointer here? These are high-N Rydberg molecules, so very near the ionization potential. But otherwise, it's a completely disordered gas. I'm going to assume in my idealized picture that this gas is quenched, 10 to the 7th molecules and a little volume about a millimeter cubed. That creates a density of about 10 to the 10th per cubic centimeter and a distance, an average distance between particles of about 3 microns. Now, these are molecules. In my case, they'll be molecules. I'm going to be talking about nitric oxide. These are molecules with larger than life physical properties. The orbital diameter of these states is of the order of a micron. They have enormous dipole moments, enormous dipole-dipole interactions. 30 kilodebye is typical. This creates a representative coupling matrix element of 2 gigahertz. And the range of disorder that I've got here, the range of energy over which these states occupy and can sustain dipoles, is of the order of 500 gigahertz. Now, I should hasten to point out that there's no laser field involved in my ideal world. So my ideal world just happens. There it is. It's there, and all of the coherences in this system are locally generated. So I don't have to worry about coherence with an external laser field. This very naturally forms a sea of random dipoles. Now, in this sea of random dipoles, I have a quantum system whose eigenstates I might choose to represent by this simple XY Hamiltonian. So a little simple XY spin Hamiltonian, in which I have spins, say I and J, that will interact with each other, that will mix, that will exchange energy, that will flip-flop if their energies conform with a resonance condition such that their difference falls within a coupling matrix element. Now, this is a system that's impossible to describe theoretically for any kind of size, and particularly for 10 to the 7th molecules. I mean, you can't even imagine. We heard something today about 10 to the 10 to the 23. I mean, we're kind of getting into this territory to try and describe quantum mechanically a system like this. So as an expedient, and just to give us a little bit of orientation, I'd like to treat this as an Anderson problem. So as an Anderson problem, I have one dipole, a random realization of the system in which I have a random dipole that communicates with all of the others. And with a given random realization and random selection of the active dipole, I have a much simpler Hamiltonian matrix to diagonalize. So let me show you some results. Let me show you some level statistics that are associated with this particular problem. So if I choose a disorder strength where my interval is confined to 500 megahertz, and I choose a coupling strength, kind of a representative average of 50 megahertz from molecule to molecule, I get delocalization. So this is Wigner-Dyson statistics. This is a strongly delocalized system. But if I go to the disorder that's inherent in this system, I have strong Anderson localization. So this is a system that localizes. It's Anderson localization. It's not many-body localization, but it's a system that localizes. Okay, so that's a kind of a toy model and a toy representation of a toy model that easily shows evidence of localization. What do we expect from a conventional notion of the behavior of a high Rydberg system like this? Well, there's plenty of experiment and lots of simulation that tell you exactly what happens. This system avalanche ionizes. So the interaction between these Rydberg molecules will release electrons. Electrons just make a mess out of the system. It ionizes, it forms a plasma. And this happens at Mott densities, densities down to as low as 10 to the 8th. And principal quantum numbers down to, here it's n equals 42. So no question about it, classically this system is unstable in the way that I've represented it. I can illustrate this maybe a little bit more graphically by showing you some simulations. So these are coupled rate equation simulations that have been validated by molecular dynamics simulations. They are really a quite accurate classical representation of the behavior of electrons, ions, and Rydberg molecules. So this goes back to Mansbach and Keck. More recently, I don't have it on here, but Thomas Pohl, Dan Vranso, and Hossein Sagdapour have refined this, again with reference to molecular dynamics calculations. This is a fairly accurate representation of what you can expect to happen classically in a system like this. Now, you'll notice I've got a little bit of an ellipsoid here. You can see these very faint blue lines. These are at a density of 5 times 10 to the 11th. These are pinning electrons that are produced instantaneously by the accident of the configuration of this system. These are in a random gas and an air-long distribution of nearest neighbors. These are molecules that happen to be close enough to instantaneously produce electrons. These electrons are going to fly through the system, and this is what produces the dynamics in this system. I've got this designed as an ellipsoid because I've got a big fat molecular beam, about 3 millimeters in diameter, Gaussian. I'm crossing it with a 1 millimeter Gaussian laser beam. This makes a cylindrical or ellipsoidal object. So here's the way this thing behaves. This is for a principal quantum number of 50, a density of 5 times 10 to the 11th, and I'm going to show you its behavior over a time period of 100 nanoseconds. What you've seen here is the behavior of the density of electrons. This is the ratio of electrons to Rydbergs in this system. That's what the color scale refers to. If you follow those little black dots on the curve, about half the system dissociates under these conditions. Remember, it's a molecule. This actually turns out to be quite important. The molecule can dissociate, so half of it disappears through dissociation. Of the half that remains, about 20% on a 100 nanosecond time scale, about 20% remains Rydberg. The other 80% forms ions and electrons. You'll notice here evidence for predissociation. This appears more evidently on a longer time scale, and the steady state of Rydberg's predicted classically falls to 0. So I've got ions and electrons, they recombine, the intermediate state lives hardly any length of time at all. It dissociates to atoms and molecules. It dissociates to atoms in this case. And a longer time scale, predissociation is complete in 100 microseconds. Now notice the electron temperature. So here the avalanche itself is releasing energy as Rydbergs relax, releases energy to electrons. This energy appears in a global sense in electron temperature and electron heating, but locally we should think about ion acceleration. So as the electrons pick up energy, they're going to expand and pull on the ions, and this should produce ion radio expansion. So this is a cartoon, probably a pretty accurate cartoon of the initial classical dynamics of this system. Okay, so let's go to experiment. So I'm going to try and show you how an experimental system behaves. This is 4,000 experiments represented on this slide. So I've sorted experiments by density, so from 10 to the 12th down to 10 to the 10th. And what you see on this diagram is a ramp field ionization. So a field ionization provides a map of the electron binding energies in the system. And you can see low density, I have the field ionization that's exactly what I should expect for a single Rydberg state, n equals 44. So these features are appearing exactly where they should be in a field ionization spectrum of n equals 44 Rydberg states. At high density, I don't see those Rydberg states. What I see are the results of this avalanche that I spoke of. So the system is behaving a bit like the classical calculation, and is showing me avalanche at high densities and no avalanche yet at time equals 0 at low densities. Now what I'm going to do is I'm going to take the field ionization ramp and move it forward in time after we use a pair of lasers to make the Rydberg gas. So we'll let the Rydberg gas evolve for a while, then sweep the field ionization ramp and detect the spectrum of binding energies in this ellipsoid. And here's what this looks like. Well, I show here electron impact avalanche. All right, now here is moving the ramp forward in time. And I'm going to move it forward out to 500 nanoseconds. So I'll show you from 0 to 500 nanoseconds what happens in this gas. In terms of the density dependence, in terms of, every measure that I would make of this over the 500 nanoseconds, it agrees very well with simulations in the short time. On a time scale of 500 nanoseconds, it agrees quite well with classical simulations, and this suggests that that's a fairly reasonable description of this system until you look at long times. So let me show you how this system behaves at longer times. So at long times, we can monitor two things by measuring the width of this gas volume as it moves in our molecular beam apparatus. So this is a time scale here of 40 microseconds. And two things about this diagram that should surprise you is, yes, it falls. It falls because of dissociation, but then it stops falling. It expands, but expands rather slowly. So slow expansion, surprising stability. And this surprising stability extends out to no discernible decay observable on a time scale of half a millisecond. I could extrapolate that and say this lives for milliseconds or longer. So this is a very surprising result. In fact, I would go so far to say that these are non-ergodic properties. So this system is not behaving ergodically, and it's as plain as the nose on your face or the type on a PowerPoint. So we have to explain this. These long-time dynamics are hard to understand. We can ask what happened to the avalanche energy, not evident in here, and also ask what stops the radial motion of these ions. We can look for the answer to this question in the images of the charge distribution that's projected in X and Y. So far, I've shown you the expansion in the Z direction as this thing has moved through my molecular beam machine. Let me show you what it looks like in X and Y. I can do this with a machine we call the plasma TV. So this is a molecular beam apparatus. If I fit it with a grid and use electron microscope ion optics to image the electrons on an imaging detector, I can see that after 10 microseconds, I have a rather unusual looking density distribution in my system. If I take out that grid and let the system fly the full half a millisecond it takes to reach the end of the detector, it looks like this. So this is what happens if I have a low pulse energy in my laser or a low initial density. Now I'm going to systematically increase the density by increasing the energy of the laser, and watch what happens to those little to this little circle. So this is a Rydberg gas made by a laser that has bifurcated and separated into two volumes. These volumes seem to indicate what's happened. These are volumes that are moving apart from one another by a velocity from somewhere between 50 and 100 meters per second. So that's what's happened to the electron energy. The electron energy that was released in the avalanche was somehow dumped into the movement, into the separation of these objects. What's the mechanism for that? Well, if you think about making an ion in an atmosphere where there are Rydberg states present, Rydberg states have an enormous stopping power for ions because they are able to resonantly charge transfer. That's not really stopping them, it's changing their identity. So as the Rydberg atom moves through, as an ion moves through an atmosphere of molecules, the transfer of an electron resonantly exchanges the identity of these two objects and effectively stops the ion cold and creates a moving Rydberg. And this kind of thing can happen over and over again. And this, we believe, is responsible for the pooling of density in these volumes and the effective transfer of individual ion energy to overall momentum of these volumes. I might point out that this process in happening quenches the electron temperature, of course. It quenches the electron energy because this energy winds up as relative velocity. It equalizes the velocities of the Rydberg molecules and the ions. We have to watch this again. It's not a bad thing to watch, I suppose. It very likely correlates the positions of the atoms in the Rydberg molecules because as they interact, they're going to be assuming their positions of minimum potential energy, and it certainly quenches their relative motion. It quenches the ion temperature. So it creates really rather special objects here in these objects that are moving apart. You should think of these as rather an exotic state of matter that happens automatically through this process. There's something more. We saw that the velocity of bifurcation depends very strongly on the density of the initial Rydberg gas that I created. But if I integrate the signal, these were raw images that I showed you. There was nothing done to adjust those images. They all looked the same. They looked like they had the same intensity. That was no accident. They have the same number of particles in them. So the system relaxes. It self-assembles to states with the same final density. They also have the same internal energy as measured by this expansion profile, which is what we always see. We always see about a 5K expansion, 5-degree Kelvin expansion is what we would associate with the initial electron energy. It's probably a mistake to assign that to the initial electron energy. That's probably the residual divergence of the molecular beam. So very low energy, and they have the same long lifetime. There's two ways that we might characterize this system, this particular system that shows up here in the field ionization as this red line. We could say that's an N equals greater than 80 Rydberg gas, or it could be a 5-degree K ultracold plasma, but neither of those limits has arrested properties in any conventional sense of the term. So let's see if we can try and describe this a little bit more fully. And now what I want to do, how much time do I have? Oh, perfect. Okay, yeah. All right, so what I want to do is take you through a stepwise field ionization experiment where I try and analyze the spectrum of binding energies for you and see what we can infer about the physical properties of the system. Remember, what I'm trying to do is tell you about an experiment and interpret that experiment physically for you as well as I can. And this is to try and stimulate theoreticians to think about this problem as you know, a system that's worth thinking about. Okay, so here's at initial time, this is, the ramp is applied with 0 nanoseconds, and what you see here are certainly evidence of an electron impact avalanche. Now, we know that this is an electron impact avalanche because we can see signs of electrons in the system, and one of the most obvious and pleasing signs that electrons are active in this system is what happens to this Rydberg field ionization signal. So what I've got on there is the field ionization signal for a 40F Rydberg state. It happens to be built on a rotational state of 2 of the ion. Now, as electrons collide with those Rydberg molecules, the easiest thing it can do is L-mix them up into high angular momentum states that have a slightly higher field ionization threshold. And watch what happens after I delay the ramp by, I think it's of the order of 100 nanoseconds. Let's just see. Okay, I want you to watch the position of these 2 field ionization resonances. Okay, in case you didn't see that, let me put them back. Okay, now watch them move to the right. All right, that's the electrons at work. That means there's free electrons in this system, and we can see them colliding with the Rydberg molecules, and this evidence shows up plainly in the field. But now watch. After 150 nanosecond, the transport in binding energy at high density stops. So look at, these are higher energy Rydberg states. These are lower binding energy Rydberg states. And watch this population as I allow the time to go forward from 300 nanoseconds. 450, 600. Predissociation is depleting the population, but the distribution of that population over the manifold of states available isn't changing. So the electron-driven energy transport stops. So the SFI experiment, selective field ionization experiment, seems to signify a population in this experiment of weakly bound Rydberg molecules. We can model this as a sea of dipoles. That's why I showed you that little hypothetical cartoon model at the beginning of the talk. Let's imagine this as a sea of dipoles and try and describe it. I've already argued that it's impossible to solve any kind of multi-body, many-body, fully interactive Hamiltonian for this system. But, so I can't solve it. But I could do what many others have done in the literature, adopt a resonance counting argument, use perturbation theory to try and help gauge stability. So scale this and test for divergence with the system size. So we want to test to see if this system shows signs of localization. Okay, each dipole sees a number of resonant interactions that scales with distance as the, just choose a distance and say, all right, on this shell of distance, I have a certain number of atoms, which is the radius of that, the radius cubed of that shell times the density, and my coupling strength out at that distance is the order of the matrix element at that distance divided by the full coupling width, or the full width of my distribution. So that gives me the probability of having a resonant interaction. Okay, notice they both scale as r cubed. The r cubes cancel out, and it says that the number of coupling events for my spin depends only on the density and delta, the ratio of the coupling width to the disorder. So this system does not diverge. This was pointed out by both Letikoff and Yao working with Misha Lukin. Okay, so this is consistent, as they said, with slow dynamics, possibly with many body localization. Now the problem with this simple XY model is that I don't include the possibility for non-resonant energy exchange between pairs, so van der Waals or Ising coupling. So I can include that following a trick that Buren has introduced, saying that in third order, if I have a couple of resonantly coupled spins, a fifth spin in the area can facilitate a coupling between those two, so long as the difference between differences is small. So they can have very different characteristic resonances, these two systems, but as long as they're both within resonance, a third body, if you will, can couple those two spins, and this adds an Ising term to the Hamiltonian. Now, I can reason physically about this system if I invoke some average properties of this Hamiltonian. So please allow me to do that. And if I do so, I can, following Buren, calculate the number of Ising interactions and see that it diverges with the coupling distance. All right, so this creates a problem for any kind of localization scenario. I've got Ising interactions, van der Waals coupling, that will cause this system to delocalize. This system will delocalize whenever this dynamic interaction between resonant pairs exceeds the average of the flip-flop energy. So let's see if I can find when that happens. I have calculations, and please don't make me go through the algebra here. I have expressions of the dipole-dipole interaction energy that I can derive from these average parameters, and the Ising interaction energy. If I just set those equal to each other, I can solve for a critical distance, or when I include the density, a critical number of spins, a very simple expression for a critical number of spins that tells me at what point I should expect the Ising interaction energy to exceed this spin flip-flop interaction energy. And what I calculate for a reasonable seat-of-the-pants guess for our system, as studied experimentally, is of the order of 3 times 10 or 4 times 10 to the 9th spins. It so happens that every time we see an arrested state, we calculate a density something of the order of 2 times 10 to the 8th. So what this suggests is that our system is delocalized until it's not. That's the suggestion. There's something more to this that, since I'm among friends, I'll speculate about, and that is the fact that this is a molecule. Now, people will tell you, in the localization business will tell you, that many-body localization is impossible regardless. If you imagine a many-body localized phase, that's subject to just fluctuations. And the presence of a thermal fluctuation in a system will thermalize its surroundings, and that will cause that fluctuation to grow. And as that fluctuation grows, it becomes better at thermalizing its surroundings, and that's the end of the story. Nitric oxide is a molecule, and I'm going to suggest to you that the molecule intrinsically opposes this mechanism of delocalization. So if I have a thermal inclusion in a many-body localized bulk, this classical region is a threat, but we've also seen that classically this system dissociates. So this dissociation causes a loss of plasma ions and energetic molecules, reduces the density of dipoles in this thermalized region until it's diminished to a void of no consequence. Okay, well, that's the end of my story. I hope I've convinced you that nitric oxide, when suitably excited, avalanches to plasma, that this plasma quenches and exhibits nominally slow expansion in which predissociation halts. The images confirm liquid-like behavior in which the plasma sequesters energy in a reservoir of mass transport. The dynamics suggest a robust process of self-organization to reach a state of arrested relaxation. That's far from thermal equilibrium, and predissociation might act to diminish the delocalizing power of Griffith regions. So with that, I'll thank the hardworking people who did all of this, and thank you very much for your attention.
Time for a few questions.
Thank you. Very interesting talk. What